Is it right? Is it right that you always wanted to know how to add stochastic movement in your Kalman filter? The time has arrived. In this video, we are going to do exactly this thing, how to incorporate stochastic movement in Kalman filter. And by stochastic, I mean movement that contains uncertainty, and how to incorporate it well into the Kalman filter. So if you remember, in the last unit, we talked about the update phase, how to multiply two Gaussian together to get a better accuracy or a better Gaussian. Now we are going to deal with the move phase. So let's start with a simple example. Assume that I have a vehicle in 1D domain and its PDF is a Gaussian around mu1 with uncertainty sigma 1, or if you want sigma 1 square. Again, I don't know where the vehicle is, but mu1 is the best guess, or the guess with the highest probability. What happens when my vehicle is now moving 10 meters to the right? If you remember from the histogram filter, if the movement is 100% accurate, so I will just shift this Gaussian 10 meters to the right. So the new mean will be mu1 plus 10 meters. Since there is no uncertainty in the movement, the new sigma will be exactly sigma 1. I didn't increase the uncertainty, but I also didn't decrease it. Why? The uncertainty cannot be lower than the prior because I didn't add any new information. But what happens if the movement has also uncertainty? I command the vehicle to move 10 meters, but sometimes it moves 8 and sometimes 11. Why does it happen? Because it is possible that the engine will go faster and slower, or it could be that when we arrive something happened, or I don't know. There is always uncertainty in our world. Therefore, when I command my robot to move 10 meters, all I can say is that the best guess is that my robot actually moves 10 meters, but I cannot be 100% sure. In order to work with the Kalman filter, I need to be able to describe the movement or the uncertainty in the movement using a Gaussian PDF with mu2 and sigma 2. But what does it mean that the movement is Gaussian? If my motion, for example, has mean of mu2 equals 10 meters with standard deviation of sigma 2 equals 1.5 meters, so I mean is the following thing. If you remember the 68, 95, and 99.7 rule, so basically, if I command the vehicle to move 10 meters to the right, at 68% of the time, I will finish with the movement between 8.5 and 11.5 meters. And in 95% of the times, the displacement will be between 7 and 13 meters. So the Gaussian nature, the Gaussian characteristic of the movement says two things. One, that most of the time we will be in the vicinity of the mean. And another thing, which is extremely important, that the error, the mean, the expected value of the error is 0. In our example, the probability to move 8 meters instead of 10 equals exactly to the probability to move 12 meters instead of 10. So plus sigma equals minus sigma. So the new posterior distribution will be now Gaussian with mu3 equals mu1 plus mu2, and sigma 3 square equals sigma 1 square plus sigma 2 square. This is how I can incorporate the new uncertainty into the prior belief. So I have a prior belief represented with mu1 sigma 1. I have a movement which contains uncertainty mu2 sigma 2, and the way to add them together is to just add the means and add the variances. The last variance equation stems from the fact that if x and y are independent random variables, the variance x plus y equals to the variance of x plus variance of y. And therefore, if I want to draw this, the Gaussian will be lower from the original Gaussian because sigma 3 squared is bigger than sigma 1 squared. And this is the idea of Gaussian motion. This phase can also be called addition because in fact I'm combining the averages and the sigmas of two Gaussians. There is another name for this, and this name is convolution, because I go point to point and move every point from the initial prior distribution to the posterior distribution. The mathematical process of moving each point is called convolution. In the next video, we will talk about that update increases the certainty in the system and the movement decreases the certainty in the system. Why? Because the new variance, the new uncertainty is bigger than the prior uncertainty, than the prior variance. We add the uncertainty of the movement. Therefore, movement in Kalman filter or in any Bayesian localization filter always decreases the uncertainty. And yet again, please remember that in order to work with the Kalman filter, the movement model must be Gaussian. And it must be Gaussian in a way that the expected value of the noise is zero. The probability to overshoot equals exactly to the probability of undershoot. This is extremely important.